Okay, now that we have seen a little bit about how arrays are declared and used in the C language, let's look at a very specific case of arrays, the use of arrays in C, which is a very common and very useful form of array that we use, we need in any programming language including C. And as a result of which there are several functions that are written explicitly to deal with these kind of arrays. The arrays that I am talking about are character arrays, otherwise known as strings, right. A string is essentially anything that we understand as text, right. It could be English text, it could be in other languages, but primarily it is something that shows up as human readable text. Okay. At the end of the day, the strings that we are dealing with are also just a sequence of bytes present in the memory of the computer, and how the computer interprets and prints these out also finally depends on various parts of the operating system, the programming language, and a few other things that are all interacting together. So let's look at some of those specific cases. So like I said, a string can be thought of as just an array of characters, right. And the important thing to keep in mind is that in the C language there is no string data type, right. In other words, there is no, unlike int or short or char which are built in data types in the C language, there is no string specifically. And the way that C deals with it is by simply saying that if you want a string, it is just an array of characters, right. So you can use a char star, why bother with a separate data type for string, okay. And given the origins of C and how it was originally written, etc., in most cases the array of characters, the characters are usually 8-bit ASCII characters, which means that basically it is an array of bytes, right, and accordingly you interpret them and print them out and so on. And now the interesting thing is, when you say that it is just an array of characters, the important thing is, strings can be of different lengths. After all, one person's name need not have the exact same number of characters as another person's name, right. A string like IIT Madras has a different number of characters than IIT Delhi, right. BS Electronic Systems would have a different number of characters from BS Data Science, right, or anything, a person's name, their address, anything that you want to print out, a piece of news, right, whatever it is, each of those are all valid strings that have different numbers of characters in them. So then the question becomes, how do we actually know how long a string is, right? And in C, the decision was taken that a string will be considered as a sequence of bytes, and the moment you encounter a byte that contains the value 0, in other words it is called the null byte, that will be treated as the end of a string, that is called the terminator, right, the string terminator. So essentially C has this concept of what is called null terminated strings, right. So somewhere in the middle of a string, if you have a byte which has the value 0, that indicates the end of that particular string. Now this has a lot of implications, some very few good, but plenty that are not so good and potentially even dangerous, right, which is why the entire business of how you handle strings in C and the functions for handling strings in C have undergone a lot of evolution and a number of changes over the years. Anyway, a few different ways in which you can define a string, right, and how you sort of identify the size of a given string, right. What happens is that, let us say you declare something as char 100 S1, where S1 is the name of the string, right. Now this is nice, right, the compiler exactly knows that you want a character array of size 100 bytes, that is exactly what this means, right. Char is of type byte, which is basically 8 bits. So char 100 is an array of exactly 100 bytes, and you have given it the name S1. So it will find a location in memory where it can find consecutive 100 memory locations that are free, that have not been allocated for anyone else to use, take the starting location of that and put that into the variable S1, so that S1 now points to that location. Now what happens if I declare something like this, char star s2 equals hello, right? Now this is kind of interesting because if I ask for the size of s2, right, at this point it is not going to give me the size of the string, right. What it is going to give me is the size of s2, which is a pointer to a character. And as we already know, in the C language, right, on a 64-bit machine at least, all pointers have the same size, right, and on a 64-bit machine that would be 8 bytes. So the size of s2 function over here would actually give us the value 8 bytes, right. And a third option is that we can declare char s3 equals something else, right, where here s3 is now effectively, yes, it is a char pointer, but this is declaration is more like the first declaration where s1 is declared as a char array, right. So in other words, s1 over here is treated as an array of characters, s2 is a pointer to a character, right. So this is one of those places where there is actually a difference between how an array and a pointer are interpreted. This third case, s3, is also treated as an array, not as a pointer, right. And what it is doing is it is going to say that okay, s3 is an array, and when you ask me for size of s3, I assume you are actually asking me for how many elements are present in the array, how many bytes are present there, and that is what I am going to return. Okay. So let us take a look at that. So this is just the code that we looked at briefly, a slight variant of the code, right. So basically what I have got is char star s1 equals hello world 1, right. So it is a static string that has been declared out here. Char s2 looks almost identical, right, because it is also defined as just something which has been given a value out here, and char s3 is similar but has one slight difference in the sense that over here I have declared s3 to be of size 10 elements, right. But if you look carefully at it, you will realize that the string that has been given to it is too long, and in fact the compiler has already observed that and has given me a warning. As you can see, it says initializer string for char array is too long, right. I have declared the char array to be of size only 10 bytes, but this has clearly more than 10 bytes. How many exactly? Well, we will see. Okay. One other thing you need to keep in mind over here is that this \n character, right, even though it looks like 2 characters when we type it in, this is actually a special type of character that we find in C. It is also there in most other languages. It is pretty much a sort of standard as far as how strings are handled in most computer programs at this point. And this / is what is called an escape notation, right. And the reason we have it is we would like to have a string where of course there are normal characters like H, E, L, space and so on, right. All of those are things that we can visually see when you print it out on the screen, and there are some other characters that do not actually show up as visible characters. \n or the line feed or the new line character is one of them, right. So the new line, the term new line actually comes from the era of typewriters, right, which most of you probably have not seen a typewriter, but what happens in a typewriter is that when you have reached the end of a page, you actually press a specific key that takes you to the next line, and what that does is it actually pushes the entire paper up by the space of one line, and it also returns the carriage, what is actually being used in order to print out the letters, to the beginning of the line. Okay. As a result of that, this new line character used to have multiple different names. It would sometimes be called new line, sometimes it would be called CRLF, which is carriage return as well as line feed. Carriage return basically means bring the typewriter carriage back to the beginning, line feed means scroll up by one line, right. And you might occasionally come across these kind of terminology in various different places, sometimes even in editors, where you see that line endings are LF or CR or CRLF, right. Bottom line is that for most cases you do not need to be concerned about those, but there can be scenarios where you come across those terms and you need to know what they are referring to. in our case what happens is I don't have a proper way of actually encoding a new line, that is to say, go down to the next line as a specific character inside a string. I don't know how to type it, right? So this \n is sort of a code which says if you see the two characters / followed by n, it means a new line, and it turns out that in the ASCII code they have actually got a specific code for that new line character. So the new line is actually a specific code in the ASCII set, right? So that \n translates into one single byte, one character, right? There are several other such escaped characters, \t for a tab space, right, which is basically an arbitrary number of spaces up to the next tab character, once again from the typewriter domain, right, which also translates into a single character, right. So there are a few different characters of that sort which are encoded in this way, right, and all that you need to know is that yes, there are certain kinds of characters which are encoded like this. A full list of those is available as part of the standard documentation of how C strings work, right, and some familiarity with that is needed in order to work with strings in C. Now as far as we are concerned, the important thing at this point is that for us \n corresponds to a single character. Let's see what happens when we actually try and identify the sizes of these different variables S1, S2 and S3, right, and try and understand what exactly is being referred to out here, right. So let's run this. What it does is it declares three variables, char star S1, char S2 array and char S3 array of 10 bytes, and then all that it's doing is it's not accessing them or doing anything like that, it's just printing the sizes. Once again the squiggly orange line, the warning is basically because I am trying to print them as integers, whereas they are actually unsigned integers, right, unsigned long rather. I am going to ignore it for now and just run the code. And what you can see is that the first one, size of S1, right, hello world, it prints out as 8. Now why is that? Because S1, right, even though it has been initialized with a string of characters and looks like a character array, S1 is actually a pointer to character. And when I ask for size of S1, what I am getting is the size of a pointer, and on a 64-bit machine the size of a pointer is 8 bytes. That is why this number 8 shows up over here, right. What about S2? It looks very similar, but because of this notation that I have over here, S2 with square brackets without anything inside it, that is okay, it is still accepted by C. The S2 is now known to the compiler as being explicitly an array, right. It is basically the difference between declaring an int star versus int a of something, right. Int star a explicitly means that a is a pointer to an integer, but int a of something means that I plan to use that array notation a of something in order to access a value, okay. Now the interesting thing is it looks like an argument over semantics, because I can actually go ahead and access S1 of 0, S1 of 1 and so on. I can use the array notation, I can use the square brackets in order to access the nth character inside S1. There is nothing preventing me from doing it, right, because after all that translates into is it takes the location of S1, or rather the address pointed to by S1, adds I bytes to it and dereferences it, takes the star operator, right. So all of that will work. Why exactly should S1 and S2 be treated as one is a pointer, the other is an array? Well, that is sort of a decision that is there as part of the language. It is something to be aware of so that you do not end up getting confused by what the size of operator is returning, but that is about it. It does not really change the way you use the functions, okay. And the third one, right, S3 has been explicitly declared to be 10 bytes, and what happens as a result is, even though you have this hello world 3 which clearly is longer than 10 bytes, right, because HELLO itself is 5 bytes, there is a space and then WORLD is another 5 bytes. it's more than 10 bytes total, okay. So clearly this string is too long, but it tells me that the size of that string is only 10 bytes because it was declared to be 10 bytes in the original on line 98 where I actually declared S3, okay. Just on a related note, of course, how did the size of S2 come out to be 15 bytes? Let us make sure we understand exactly what is happening out there. H is 1 byte, HELLO is 5 bytes, right, because this is just plain ASCII characters. The space is the 6th byte, WORLD, we have 11 bytes, there is a space 12 bytes, there is the number 2, 13 bytes, and this \n, like I told you, is a single byte, it is one character in ASCII notation. So I end up with 14, but remember that strings also have to be terminated by a null. There is one more byte that is added on automatically so that we can have a 0 at that location, and it becomes the null character that terminates the string, and therefore I have size 15 for this array S2. That is how I end up with this number 15 out here. Now, as you can see, we have declared 3 different arrays, S1, S2 and S3, and the printf format notation, right, this %s essentially takes whatever you have out here, treats it as an array of characters and will try and print it out, okay. So let us see what happens when I print out each of these 3 different strings. What I can see is S1, right, even though it said that size of S1 was 8 and S1 was a pointer and so on, it worked perfectly fine. It basically picked up this string hello world 1, put that in correctly over there and printed it out, hello world 1. You might notice that there is one extra blank line out here, and in case you are wondering why that is the case, it is because there is one \n coming from the string itself and another \n that I put in out here, okay, that ideally one of them should not have been there, right, but it does not matter, it serves to illustrate a point, which is that if you have two \n's, there is one \n which went down after the one to the next line, there is another \n that went from this line down to the S2 line. So there are two \n's effectively that have appeared over here. Okay, so far so good. Now what about the next one, S2? When I print S2, I go ahead and say S2 is equal to hello world 2, that is also good, right. As expected, there is a \n out here and another \n immediately after that on the next line as well. S3 is where things get a bit tricky, right. What happened? I actually try printing out the value of S3 and you can see it starts off fine, right, hello world, up to this point is okay. What's special about the L? It is the 10th character, the 10th byte, right, HELLO space WORL, that's 10 bytes, which means that anything else that was there beyond this, which is the D space 3, the new line character and the 0 that was used in order to terminate the string, are all technically outside S3, right. When the initialization was done, what the compiler did was it only copied the first 10 characters into S3. All of those 10 characters got their correct locations, as you can see here. The problem is the null byte, which was supposed to terminate the string, did not actually get copied into S3, right. And what happens as a result is you end up with some garbage characters out here. We do not even know what this corresponds to. It became a G and this is something that basically could not be printed, right. The \n that I had over there is gone because it should normally have forced me to go down by a line, but luckily it looks as though at some point I quickly encountered a byte which had the value 0, right. How do I know? Because it actually printed the end of the string and moved on. Potentially you have the danger that if there were no zeros present in your memory at that point, it could go on and on and on and try to print out an extremely long string. That is a potential danger. The C language, the normal printf and so on, do not have any built-in safeguards to prevent you from doing something like that, right, which is potentially one of the sources of security holes and bugs and all the kinds of vulnerabilities that you hear about every now and then in code. Okay. Now, to understand this a little bit better, let's go ahead and just print out a little bit more about these strings, right. What I am going to do is I am actually going to print out the first 15 characters, right, of each of these strings, right. Why 15? So that it's at least long enough for so that I know for sure that I am able to print out the entire string that I have, right. So what I am doing is I am printing S1 of I, and I am printing it both as a hexadecimal character and as an ASCII character, in other words interpret it. So this first S1 of I will show me what the number, the numeric code corresponding to that character is, and the second one will actually show me what it gets displayed as. So let's take a look at that, right. And what you can see is, by the way, you might notice that on this occasion the S3 went up to a hello world and then afterwards something just disappeared. It did not print that strange character at the end, interestingly. Okay. Now let's look at what got printed after that. S1 of 0, it says has the value 48. Now this 48 is actually hexadecimal, which means that in decimal this is actually the number 72, right. So because 4 is 16 into 4 plus 8, so that's 72 decimal, and that is the ASCII code corresponding to a capital H, right. S1 of 1 is the hexadecimal 65, which is the letter E. Then S1 of 2 and 3 are 6C, which is small l, 6F, small o. The character 20, right, in hexadecimal or 32 in decimal corresponds to a space. Then we have 77 hexadecimal, which is W, and so on, WORLD, once again a space. The number 1, which has an ASCII code of 31 hex, which is basically 49 decimal. And then S1 of 13, right, the 13th character, or rather the 14th character in the string, has the value 0A, which is decimal 10, and you can see that it got printed out as, there is the starting quote is up here on this line, the ending quote is on the next line. What that indicates is that it actually tried to print out the character as a new line, and it went from one line to the next. It literally printed it out as a new line. Okay. And finally, of course, S1 of 14 is 0. That cannot be printed, right. When you try printing it, it basically does not show anything in that gap over there. It literally puts the two quotes next to each other. This is not a printable character, but on the other hand, it is also treated as the end of a string. So it does not lead to an error, right. So you can see that S1, for example, is very clean. It has all the 15 characters from 0 up to 14 exactly as expected. Let's see what happens with S2. And when I run this, what I find is, once again S2 has the same hello world. Now it is 2, which has the hexadecimal 32 as the code, and S2 of 13 of course has the new line character, S2 of 14 is the null character to end the string, right. And finally, let's try it with S3. And here what you can see is S3 of 0 starts off as H, E, LLO, etc., right. I go up to S3 of 9, all the values are correct, it has been initialized properly. Luckily in this case, S3 of 10 had the value 0. Why did that happen? I don't know. I think it's just plain luck in this case, right. It turned out that S3 of 10, S3 of 11, 12, 13 and 14 were all 0. There is absolutely no guarantee of this happening in general. In fact, as we saw the first time that we ran this, we ended up with some unprintable characters out here, right, some strange characters that did not make sense. Okay. In this case we were lucky because the moment that S3 of 10 was seen as a null character, the printf worked exactly as expected. It printed up to hello world, right, stopped at the 10th character because the 11th character turned out to be a null, and it treated that as the end of the string. But that is just pure coincidence, right. And in general, if we run it again, it looks as though the majority of the time, probably for whatever reason, the memory is initialized to 0, but there are no guarantees as such. So now, since S1 and so on are arrays, right, let us look at what happens if we try to change the value of an array, right. What I am doing over here is I am basically taking the S1 of 0, and S1 of 0 should be pointing to this character, the capital H, right, and let us see what happens if I try printing that out. As you can see, what ended up happening over here is I tried changing the value, right, and then printing it out, but it has actually not changed the value at all. It ended up just retaining the other, the old value that was initialized over there, right. So what has effectively happened over here is that this hello world 1 \n and so on is a particular area in memory that has got initialized to a certain set of values, right, and trying to change one of those directly in general is essentially gets ignored by the compiler, right. It treats this as a special kind of an array. It does not allow you to change those values. It does not, for whatever reason, create an error either, right. On the other hand, the char array S2 that has been declared out here, right, when I have declared it as an array and I try accessing S2 of 0 and changing the value that I have out here, you can see that that actually ended up changing the content, right. So this is more sort of an artifact of how the compiler works, right. The bottom line is that if I declare something as a char array out here, or rather a pointer to a character, it sort of implicitly takes it as this being some kind of a constant string that is present in memory and just treats that as a pointer over there. It does not allow you to change it, right. On the other hand, I can go ahead and if I have declared a string explicitly like this, which is a character array, then I am able to change that value. Okay. This, like I said, is more an artifact of how the compiler works. It is not very, there is not a good justification for exactly why it should be this way and not some other way, but it is something to watch out for. You need to be careful about how you declare strings. In particular, when you are trying to sort of work with constant strings that you have declared and you are trying to modify them and so on, you need to be aware of how to declare them, and it is always safer to declare a character array as a set of bytes of a given size and explicitly as an array rather than just as a pointer. So one of the observations with regard to how we use strings, as we already saw with the previous example, is that the bounds checking as such is not really enforced, right. We already saw that I could declare something as S3 of 10, right, 10 byte string, and because of the fact that I did not explicitly put in the 0 bytes over there, just by accident it turned out that I had a 0 byte after the 10th byte in the string, so I was lucky. But if I did not have that, it was entirely possible that I could somehow have read past that string and continued onwards, right, and we will see some examples of that later. Now what that means is that even though I have declared something as being a string of length 10 bytes, it is possible that in a printf or a scanf I actually end up going past that and reading past the value of what I expect, right. And this becomes especially problematic in applications that are what are called user facing, right, where there is somebody, not the programmer, not the original programmer, who might be using the application, and this is actually the majority of all possible programs, right. Most programs that are written for distribution to others or for a web based audience or anything like that are user facing. Now what that means is that you could potentially get malicious input, malicious meaning that they are trying to crash the system, or even worse, to try and find out secret information from the system, information that should not be revealed to them, right. And because this reading past the end of a string or just eliminating the end of a string is possible in C, it can lead to all kinds of complications, right. There are many issues in the language that are related to this, due to which there have been a number of changes actually motivated in the language itself. some of them, I mean some of the issues themselves we will look at, but the exact changes and how they have been dealt with in other languages is well beyond the scope of what we can look at in this course.